So look, thank you very much for joining us for this second Cavalier lecture of the academic year. So it's a real honour for me to introduce Professor Reinhard Genzel from the Max Planck Institute for Extraterrestrial Physics in Munich, where he's the director. Sadly, due to last-minute unforeseen circumstances, Reinhard wasn't able to travel and be with us here today. But I'm very glad that he's agreed to give his lecture online instead. So that's very good of you, Reinhard. Thank you very much for doing that. I think Reinhard really does need little introduction. We always say that for our speakers, but I think it's particularly true in this case. But he's a pioneer in the development of very sensitive instrumentation for infrared and submillimeter astronomy, with a particular interest in observing the structure and activity of the Milky Way and other galaxies. He's perhaps best known for his work studying the orbits of stars and the infall of gas in the galactic center, and that's work that provided compelling evidence for the existence of a supermassive black hole right at the center of our galaxy. And for this work, he was awarded the Nobel Prize in Physics in 2020, jointly with Andrea Ghez and Roger Penrose. So, in addition to the Nobel Prize in Physics, Reinhard has received numerous awards and accolades over his long and highly distinguished career. These include the Shaw Prize, the Crayford Prize, the Herschel Medal from the Royal Astronomical Society, and many, many more. He was elected Fellow of the Royal Society as a foreign member in 2012, and he holds honorary degrees from the Universities of Leiden, Paris, and Grenoble. And Reinhard, there may be more that I've missed. Apologies if that's the case. So, thank you very much for accepting our invitation, Reinhard, to give this Cavalier lecture. And we're very looking forward to hearing what you have to say about the status and future prospects of experimental studies of black holes. So over to you whenever you're ready.
Okay, well, thank you, Anthony, and dear colleagues. I owe you an apology, of course, that I in the last moment I had to cancel my trip. I'm certainly be happy to come later when everyone has time and so forth, but today it was not so good to make that trip. So this talk really is a rather more general talk. The title, Experimental Studies of Black Holes and Galaxies, I really mean experimental. So in a sense, let me distinguish that a little from classical observational astronomy. And I wanna in this talk, given the subject of black holes, try to get across, if that's needed, with an audience like you, that we are in a very, very special time now. Remarkable, in that with three different approaches, interestingly, all hinging in the end on interferometric technique, Michelson's techniques. In the near-infrared, on the VLT, with radio astronomy in the EHT, and with gravitational waves, currently ground-based in 3 different sites. The problem of black holes, which were, of course, 100 years old in terms of the theory, has turned from speculation to true experimental physics. And I find this, at least for myself, a remarkable thing. I mean, we are really doing physics in space, and we are, as I will try to show you today, we are asking questions which we wouldn't have dared even thinking about, say, 20 years ago. Now, this story, in all of the 3 aspects you see there, is none which you do overnight. The technology which had to be developed in all of these cases is enormous. And that has to do with the fact that we're looking at distant objects. We want to have a very high precision measurements for the electromagnetic pieces of evidence. We're looking for precisions on the order of a few to a few tens of micro arc seconds. And for the gravitational waves, of course, we're trying to see currently in stellar black holes, but in the future also with massive black holes, the photosphere around a black hole. So that's really a tough challenge, and that's why it is taking so long. I mean, I myself started on this path with Charlie Towns in Berkeley. I'll mention briefly Charlie's role in this in the end of the 1970s. And also in VLBI, I worked in my thesis on VLBI when we were still doing centimeter wavelength work and not 1.3 millimeters across the entire globe. So this is fantastic progress. Likewise, in the gravitational waves, you know that. So this is really a very special time. We're going from the predictions, the glorious predictions of Albert Einstein, Schwarzschild, Penrose, Hawking, and Kerr, and others, to the real question of whether we can confirm or not these predictions, including their more subtle parts. And I'll try to touch on these more subtle parts and not just sort of say, oh, yeah, we've seen something compact. No, we want to go further than that. We want to really, truly ask the question whether the objects which we and many other astronomers are looking at, observing in different wavelengths and so forth, in AGNs in particular, are indeed Schwarzschild-Kerr black holes. Now, of course, as you know, the early observational part of this started, well, in Cambridge. And following the discovery with radio astronomy techniques of bright radio sources, this one, 3C273, was one of the first very bright ones, which on optical pictures, as you know, look like relatively faint stars. Now there's this smudge there in the upper left of the picture, and of course that turns out to be a relativistic jet, which is transporting relativistic particles away from the central object. Martin Schmidt with a Palomar telescope then showed spectra of the central quasar to show extraordinary redshifts for the time, 16%, which interpreted as expansion of the universe means that this object is about 2.4 billion light years ago. At that time, a sensation. You know all of this, I'm sure, followed by a decade of, on the one hand, more discoveries, ever further objects, ever brighter, such that it became clear that there must be an energy source in here on scales of a few light years, which produces 1,000 to up to 100,000 times more energy than an entire Milky Way. So that's extraordinary. And of course, the theory done to a significant extent in Cambridge, discussed all the different options. And indeed, early on, through Martin Rees and Donald Lindenbell, opened up the discussions toward accretion of material at high rates onto very massive black holes as one of the ways to generate 1,000 times more efficiency in electromagnetic radiation production than what was known to occur in stars. So that was the early story. And I'm sure some of you will recall that the question was next, well, how could you prove that? How could you possibly prove that, given that these objects are so far away? What is obviously the case here, that you're predicting that there must be a very highly concentrated mass with an event horizon, which is solar system scales or smaller. And how would you use gravity, which is the key quantity, to test whether such mass concentrations exist? And it was clear at that time that you couldn't do that at the distances of quasars. I'll show you today that this is not true anymore. We actually can now measure kinematics of gas in a resolved fashion at distant redshifts. So we have moved, in fact, the experimental capabilities from the local universe to the high redshift universe. Now, in the famous paper in '71, Lindenbaum and Rees hypothesized, well, if quasars are sort of the iceberg, the tip of the iceberg, where they're just so bright because they're accreting close to the Eddington rate, well, then maybe other galaxies might have such massive black holes as well, millions to billions of solar masses, but are not accreting that fast. So in that sense, maybe even closer galaxies might have that, where we then, the techniques available at the time could indeed measure motions of gas. That's what would initially Lindenbaum and Rees proposed in '71, or then later on stars. So that's how the whole hunt started getting going, to start measuring in nearby galaxies and nearby AGN, not quasar class, but Seyferts and so forth, motions of gas clouds through spectra, Doppler motions, but then also through proper motions. And this is the story of one side of this talk. Now, of course, that culminated in the last 30, 40 years, in my own case, in using initially the gas, but then the stars. And the remarkable story of being able to measure stellar motion so precisely that we can see their orbital motion very close to the black hole. You'll see where we are on that story, seeing their motion on scales of less than 100 astronomical units, where their motions are truly extraordinary, like almost 10% the speed of light, and even further in, which is, of course, where one would like to go if you want truly see that this is an object which has an event horizon. And in the galactic center, where we are talking about 4 million solar masses, that event horizon has a diameter of 20 microarcseconds. So that's not very large indeed. And so how can we tackle that? Now then, of course, came the fantastic breakthrough in the mid-20s with advanced LIGO, of being able to measure inspirals of stellar black holes, and really truly seeing the merging of these two stellar black holes into a single hole, thereby giving really truly compelling evidence that such things as stellar black holes might exist. But let's be clear about that. What is not clear from these measurements is whether these are Kerr black holes, whether they truly adhere to the metric proposed by Roy Kerr and Schwarzschild, etc., or whether there's a twist near the event horizon, which makes the interpretation still slightly different. So we have to keep that in mind. Then the same story, in a way, with VLBI. I mentioned that already in the 1970s. Distant quasars were looked at with VLBI and the cores of them observed. But then over time, it became clear that if one wanted to see the photon orbit and the bending of the light right next to the black hole, one has to go to very, very short wavelength, and at the same time to baselines of Earth diameter. Now, I won't talk about the technologies here involved, just emphasize that they truly are, I would say, imaginary and also very, very difficult developments, and we as astrophysicists can be proud of. Not that this is actually so clear to all of our physics colleagues. I've had even recently very interesting discussions with physicist colleagues, Nobel laureates, where I wanted to tell them about the LISA experiment, which I will come to at the end of the talk, and that one with such an instrument could even for massive black holes do extreme mass ratio inspirals, and thereby test the no-hair theorem really accurately. And my colleagues, believe it or not, would answer, well, yeah, but everyone knows that general relativity is correct. Why are you trying to do this? This is so expensive. So there you see, it's actually, you know, there are different sides of the story, and that has to do with the fact how serious you want to take any kind of alternative proposals which have been made by a number of theorists other than black holes. And here's a whole collection where, of course, on the horizontal scale, you see size and the different classical scales, event horizon, innermost stable orbit, photon sphere, etc. And then, of course, the potential possible solutions other than black holes. Fermion balls, I will talk about those briefly, boson stars, gravitar stars, etc., wormholes. And what I will use throughout this talk as a measure of how close we are in testing the black hole prediction is this measure of compactness, which obviously is for a Schwarzschild hole, a number epsilon, which is 0, if the radius of the object is equal to the event horizon. There are other ways of characterizing, of course, black holes, but this is one which, the easy one, which I will use since it's actually moderately easy to measure if you have resolved spatial measurements and if you have a measure of the mass through motions of a test particle. Now let's talk about the first one of those, and that's the galactic center. I will not in detail and don't have the time go through the various stages over these last 40 years of improving the technology. You know, we started off with relatively small telescopes. Then the key thing was to get to imagery in the near infrared, because the galactic center cannot be observed in the optical because of foreground dust. In the near infrared with detectors, which when we started in the 1980s were not available. The American military had them, but they were classified, and it took a long time to actually get that technology into the civil sector, and then improve over them over time to spectacular detector systems, imaging detector systems, which you now have on all the big telescopes. Now, obviously, going to big telescopes is the second big step. Both the KICC and the VLT are, at this point, sort of the best pieces, but you all know we are currently in the Atacama Desert building the ELT, a 40-meter telescope, and our institute has the privilege, but also the the stress to build the first instrument for the ELT. So with the 8-meter telescope and the technology of adaptive optics, which basically, if not eliminate, then at least lessens the effect of perturbations of the wavefronts by the Earth's atmosphere, one can then go to diffraction limited resolution, which for an 8 to 10-meter class telescope in the near infrared is about 50 microarc signals. And then in the 2000s, we started thinking about whether one couldn't take the next step. Coming from radio astronomy and having grown up in VLBI, I felt, well, maybe we could use the 4 telescopes of the VLT together as an interferometer. That was planned in from the beginning, but to actually make that possible at the limit for the galactic center in terms of sensitivity and precise measurement took more than a decade. Frank Eisenhower was the leader of that, and has improved the sensitivity of optical interferometry available throughout the world by about a factor of 10,000 at this point. Now, Andrea Guess and her team, of course, at the KICC, carried out wonderful measurements with the KICC telescope in the 90s and onwards at about the same time as we did. And the two teams have had a mostly friendly, but sometimes, of course, a highly competitive situation. But that's good for you as the audience listening, because you can immediately see if one of us says something, whether the other one also gets a similar result or not. Mostly we do, sometimes we don't. So that's the fate, of course, of experimental work. Now, when we started in the 1990s with the stellar work and on the smaller telescopes and without adaptive optics, the first infrared imagery would look like this. Now, this is a scale of about 3 arc seconds in the galactic center. So that's about 0.1 parsec with the camera at 2 micrometers in seeing limited conditions. Now that red circle there in the center, that is where we think the center of the galaxy is, based on radio observations, which were available before that time already, and showing that there's a very compact radio source we call Sagittarius A star. Now, what we saw was obviously some very big stars, which you see there, which later turned out to be O and Wolf-Rayet stars, very powerful, massive stars. At the position of Sagittarius star, not much. In fact, that became so clear in the 1980s and early 1990s that many people, including Martin Rees, were not so convinced anymore that there could be a black hole. Because number one, why is there no strong infrared source? And number two, even more important, how can it be that surrounding on scales of a tenth of a parsec, this object is what is really truly the largest collection of O and B stars in the Milky Way? That shouldn't be there because of the tidal forces by the black hole. But be that as it may, with adaptive optics, we could now go from the smeared out imagery to much sharper situations and look in the very center and beginning, let's amplify this a little bit, it's, obviously a visible concentration of fainter objects near Sagittarius star. So these little stars are the star of our show nowadays, not the big ones. It's the little ones because they are really truly close, and they are the ones which have given us the extraordinary evidence on their motions, orbits, and on the mass distribution. So this is with an 8-meter or 10-meter class telescope. Now in the interferometry, you go from 8 meters to 150 meters. So you'll gain another factor of 20. So with gravity, the interferometer with the VLT, we can now zoom into the central region. And there's a picture from 2001. Sagittarius star itself is now visible in the infrared all the time, highly variable. And you see faint stars surrounding Sagittarius star and moving very fast all the time. Currently, there are, this summer, there will be 3 fairly substantial stars doing a pari. You see there's one star actually very close to Sagittarius star that appears to be inward bound, at least on the sky, and you're wondering whether you might see lensing as the star comes close. So these are the tools we have available to us. And with these tools, the two groups over time, in 30 years' time, improved the measurement of velocities, both spectroscopic velocities on the hydrogen recombination lines, but also the astrometry from their position on the sky. And you see sort of the current state. The remarkable thing on the right side was the discovery that one of the stars we had initially not so bright actually, S2 or S02 in UCLA terms, was moving ever faster in the early 2000s and parried near Sagittarius star, which is down below in this black dot, only 15 light hours away from Sagittarius star. 15 light hours. So that's about 3 times the orbital radius of Neptune, and had a velocity there in early spring of 2002 of almost 8,000 kilometers per second. So if you do Newton, in any way, shape, or form, you will find that there must be some object there of a few million solar masses. Now, we had known that there was about 4 million solar masses in the broader vicinity from measurements of gas cloud motions a decade earlier in Charlie Townsend's group. But now we are sort of pushing this inward and thereby eliminating ever more possibilities. Now, having seen this in 2002, we immediately realized, oh, wow, okay, this star has an orbital period of 16 years only. Remarkable, 16 years, like in the solar system. And so it'll be back in 2018. And if we then had a further improvement in resolution and astrometric precision of substantial nature, well, then we could actually begin to test general relativity in these extreme environments around a massive black hole. So that's why we started the development of gravity in 2005, convinced ESO to let this happen. And in 2016, we were ready. And then the color of the data points are not red anymore, but blue. That's the measurements with gravity. The Perry happened in 2018 May, on the 19th of May of 2018. And indeed, there it was. We could see the motions from night to night of the star and precisely determine the orbital characteristics. Now, on the left side, you see that S2 is not anymore the only star for which we have full orbits. We currently have full orbits for about 5 stars. And in fact, one of them, this guy S29, is on an orbit which is even deeper than that of S2. And we have another star, which we are still working on, which may have an orbital peri of about 20 astronomical units. S2 has 120. So that's really the fantastic thing, that nature has given us stars which are on almost parabolic orbits, ellipticities between 0.8 and 0.9, probably having to do with how they got injected into the central region as binaries and then disrupted through the Hill's mechanism. That's at least the prevailing interpretation. So that is, so to speak, the data at first value from both groups. And now we can make precision measurements of the mass and the distance. And so statistical measurements are now with the interferometer down to a few 0.1 or 0.2%. With the adaptive optics is a little worse. Of course, there are systematic errors which always dominate. We can also get the distance to the galactic center with high precision by comparing the orbited to Doppler motions to the motions on the sky. And again, you see, the accuracy is astounding. So that gives us a nail, so to speak, a real prior on which we can, as you will see in the next slides, test then, the validity and the consequences of tests of general relativity with these numbers in hand. So the first one is the gravitation redshift, of course, and that in the case of S2 means that if you subtract the orbital motion due to Newton at peri, you should see a 100 kilometer per second redshift due to general relativity and another 100 kilometer per second due to special relativity, transverse Doppler. And indeed, here is the residual velocity curve over the years, the peri at 2018.3 1.38. And you can see there you have this 100 plus 100, 200 kilometers per second shift from the Newton orbit, which is the dashed horizontal line, and GR is the continuous line. So if you parameterize this in terms of a fudge factor, FGR, where F is 0 for Newton and 1 for GR, well, this is a highly significant confirmation of general relativity. Now, this is, of course, a measurement of the Schwarzschild metric, and this is not sensitive, at least at this level here, to any deviations due to the spin of the black hole. The next test we've been able to get with the interferometer, not with the 8-meter class telescope, is the fact that the Schwarzschild and also the lens steering theory with spin of the black hole predicts precessions. In plane prograde precession for in Schwarzschild, which for the orbit of S2 should be 12 arc minutes per orbit. 12 arc minutes per orbit. So that's half a milliarc second over 20 years. So not easy to get because that's where the systematic problems hit you. And most of the precession anyhow happens very, very close to Perry. So if I do a similar diagram as the one you've seen now for the Schwarzschild precession, where I subtract the orbit, the Newton orbit, then of course the Newton, only the Newton data would give you a 0, 0 all the time, right? Because you have subtracted the orbit fully. Now, for the parameter of the S2 orbit, as we know it, GR predicts these loops due to the precession. And so if you now go at this with the interferometry, as I said, the measurements of the single telescopes are not sufficient for this. You can see that we indeed confirm again the general relativity effects very well to 10 sigma about. So indeed, if you can look on the orbit, the old orbit in 2005 beyond Parrid is the red data points, and then the blue ones are the new ones, and you can see that the 16-year later orbit is just half a milliarc second displaced to the right, as predicted by general relativity. Now, okay, that's fun, and you would say, well, okay, well, that's first PPN1 corrections. You would think that's sort of obvious, but it's actually astrophysically very, very important, because if there were anything but a single black hole, it can't look like that. If there were, for instance, a double black hole, or a black hole with a substantial cluster of neutron stars around it, as many people had proposed, thousands of neutron stars, or a dark matter cusp around the black hole, which has a substantial mass, well, then you should see, in addition to the precession, the forward precession, you should see Newtonian retrograde precession. Okay, and so that's sort of the key element. I'll come to that in a second. Now, what about getting closer? So we are now at about 1,000 or 1,200 Schwarzschild radii. That's great, but how can we get to near the event horizon? And the answer is yes, with two methods currently. One is the emission from Sagittarius star itself in the near infrared, and one by the light bending of the emission around Sagittarius star by the black hole. So if you look in the near infrared at the emissivity of the central object, and you see it's varying all the time by factors up to about 30 on time scales of hours. Sometimes you see the tremendous excursions every few years anyhow, but certainly on a scale of a few days, you can see brightenings of about 2 or 3 magnitudes, and that emission here is hot gas. about 10 million degrees, 10 to 11 degrees gas, which is highly polarized, 40% polarization. So it's synchrotron emission. Now, if you look at the spectral energy distribution of Sergei star, which is on the right side there, then that's the F nu F nu distribution in the radio, which is up to about a millimeter, relatively stable in emissivity. But then as you go to shorter wavelengths, submillimeter, infrared, and X-rays, it becomes highly variable. So these flares, which you see there on the left side, then generate emissivities in the near infrared, which are way above what you can explain with the normal virial temperature of the gas. You have to accelerate. You accelerate by factors of 1,000 the electrons to get infrared emission. And for the X-rays, likewise, you need to either have Compton scattering or even stronger accelerations of the particles. So this gives us a tool now to look at the central region. So this fairly complicated slide down here on the left is actually a recording on the left side on top of X, in the middle of in Y, RA and DEC, and then in the bottom in angle of the polarization direction of the emission. And you see it's a fairly regular motion. Now this is not just one flare, this is 10 flares. We can average them. Always the same thing, a clockwise rotation which takes about an hour in orbital period of the polarization. At the same time, on the right side, the same is now plotted in astrometry. And you see, wow, okay, there's also there a rotation clockwise in about an hour, same period, of the position on the sky. Such if you put the two together, you get this diagram in the bottom where the polarized emission is happily rotating in almost every flare we've seen so far, over about an hour and once around. Now, about an hour means that, in fact, the radius of this motion is about 9 or so RG, or 4.5 Schwarzschild radii. So it's outside, a little outside ISCO, but the fact that this happens in an hour means that the motion here is at about 30% the speed of light. So if you interpret that motion in terms of a virialized motion, then of course you have a time and you have a radius, and that gives you a mass, and that mass turns out to be consistent with our prior of 4 million solar masses. But now, at 4 Schwarzschild radii. You can learn more about this. One thing you can learn is that the geometry of this black hole gas must be pretty face on. Not what people would have expected. Many people thought that the plane of the black hole, due to the, say, spin motion of the black hole, would be along the Milky Way plane, but that's not the case. It's actually at a large angle to it and almost face on. And the next thing is, you see there's one polarization rotation per astrometric position. Well, think about it. If the polarization is due to a magnetic field of the electrons orbiting there, and as most people would have expected, in this accretion plane, lie in the plane of the motion, then the U and Q parameter should show 2 revolutions per orbital revolution. So that means we can derive from this 1 orbital equals 1 polarization direction. Immediately, it's a face-on situation, but the magnetic field is more or less perpendicular to the orbit. And that really is only possible if the magnetic field energy density dominates. Because otherwise, the magnetic field lines get stretched by the motion. So that's a very interesting set of conditions. So this is what we deduce. Clockwise motion of a somewhat face-on, not fully face-on, highly irregular motion occurring every time we look at it, if the flare is strong enough. So now let me come back to what else could there be. Now, given that the Schwarzschild precession is so well behaved, we can immediately, interpret how much material elsewhere, other than the black hole, could happen. And initially, people felt there should be a huge concentration of stuff, but that's not the case. Within the orbit of S2, 2,500 astronomical unit at Apo, we find less than 5,000 solar masses. So that's only a fraction of a percent of the black hole mass. And the UCLA group gets 17,000 solar masses. But we both find the same thing if you do Monte Carlo analysis with either gravity that's on the left side or with the KICC data on the right side. You can see that the probability of having a second object is only outside of about 1,000 AU, not inside, certainly not in the region of the S2 orbit. There's very little else. Okay, now finally, let's use the photons. And so that, of course, that experiment was proposed a long time ago by a number of people, Luminet, Bardeen, and then Falke, Melia, and Algo, so that if you have a light source behind the black hole and you look at the black hole, then the light gets bent even outside of the event horizon, and thereby you see a dark region in the center, which is larger than the photon orbit. It's about 5 times the gravitational radius. And if you have detailed enough information to distinguish those rays which get just bent once or twice or even more times, then you would even see substructure. And as you probably have seen, what our colleagues in the Event Horizon group have seen and published 2 years ago is indeed this picture. Likewise, in M87, which has a much bigger black hole, but also is further away, you see the same picture there by making it very likely that this donut indeed has to do with light bending around a black hole. Now we have a prior, right? A very accurate prior. We know what the distance is, and we know what the mass is to a fraction of a percent. And so if you calculate from that what the size of the ring should be, then it should be 51 microarcseconds. Now that's pretty good. 51.8 microarcseconds is what the EHT group are finding. So again, you can turn this around into a measurement of mass, in this case at around 5 Rg, so a little outside of the photon orbit, and you get again a mass of about 4 million solar masses. So that's the current status. I should add that many people, of course, have tried arguing based on the faintness of the central region. At the same time, of course, on infall of material, that there must be an event horizon. That's a very tricky argument, and if you include lensing and so forth, it's not so clear that the faintness of the central spot is a sufficiently quantitative tool to make a statement about the existence of an event horizon. So here's the summary after 40 years in the galactic center. Horizontal scale radius in parsecs in the bottom, and then in gravitational radii on the top, logarithmic units, and the enclosed mass. And we started with towns in the early 1980s, they're at around 1 parsec, okay? That's just when the mass distribution becomes from increasing with radius to a constant value. And then we will basically measuring ever better, ever higher resolution. Then comes the S2 orbits, the fact that UCLA and VLT agree perfectly. And then finally, we can push now this evidence all the way to the event horizon. And so that sets a tremendously precise upper limit, which you see in these purple dots on any extended mass. Of course, there are stars, we see them, but they are not very much mass. So there cannot be, for instance, a very large, black hole, stellar black hole cluster surrounding it. Now, a number of people, of course, have gone further than this and have proposed, well, it may very well be that there's sort of a central mass here. Let's assume that. But could it not be that there is also a cusp of dark matter? In particular, Ruffini and his gang, but before him, Violier and Milanese had done that. And so if you have a sufficiently massive neutral fermion, a neutrino, say, then you would expect a central concentration of the cusp of dark matter. And on the right side, you see what would be expected for different masses of the dark matter particle in terms of the rotation speed. So the most favored one on the scale of dark matter on galactic, I mean large galactic scales, is sort of around a few kilo electron volts. That wouldn't give you very much of a central spike. But Ruffini group has actually proposed, well, it could be that the fermion is much heavier. And they favored initially a fermion of about 50 kilo electron volts. And if you convert that into a mass distribution, then you can see that the actual observed rotations of the stars all the way to but barely S2 could be fit also with a 50 kilo electron volt fermion ball. That's not favored on large scales, but it's a possibility. But then as you go inward and take now the flares and the shadow as a new marker, now you would have to have a fermion of about 400 kilo electron volts or more. So that's close to the gravitational collapse mass, so very unlikely to be the case. Now, this is the fermion ball scenario. The other one is a boson star, which was discussed also quite a bit in the 1980s and 1990s. There, the size of the central object is expected to be fairly small. So it's very difficult with the stellar measurements and even with the EHT and so forth to exclude that. It could be, depending on accretion rates, etc., it could be a little bigger, it could be a little smaller than what the Event Horizon Telescope has seen. But if you take this explanation as a generic explanation, a boson star explanation as a generic explanation for all AGNs, then given the accretion rates of some of the highly accreting quasars, etc., you would collapse such a boson star to a black hole. So, in my personal view, Occam's razor probably eliminates this, but we shouldn't. We should be careful. It could be we need to make more tests on small scales and obviously improve the quality of the measurements very close to the central source. Okay, so that's my start. That's the start, the story about the galactic center and how we have it right now. We have come enormously forward, and I would say we have made a pretty tight case that this is indeed a whole, whether Schwarzschild or Kerr, we cannot say. I'm coming to that at the very end. Now let's go to a more distant AGN. How can we say something about that? Well, of course, the picture of distant AGNs was very much, coming from high energy measurements, X-rays, gamma rays, then of course the optical broad line, narrow line emission regions, then the question of a dusty torus in this central region, and once you have a picture like this, then of course you might say, well, if there's a central accretion zone there, which is very, very hot, produces X-rays, there's the narrow line region and the broad line region reflecting these X-rays, then you can use reverberation of the photons to say something about the size. And that's been the tool for 30 years now, and has given enormous information. But that works for nearby, relatively modest mass black holes only because of the timescales of the photon delays. Is there a way to make a direct measurement from the kinematics of the innermost region, also in very distant AGNs? And the answer is yes. With gravity, we can do this now. The first one was the classic one, which I showed you before, 3C273. There's the Paschen alpha line, and then you see the interferometer phase, and you can see immediately that the blue and the red side of the line are in a different position by about a fraction of a micro arc seconds or some micro arc seconds. From this, you get a broad line region size, and from the motions, of course, a mass. So this is a truly rotating structure perpendicular to the direction of a jet. Almost perfect. And so that's the first one we were able to do, followed by a bunch of others. But the real interesting new territory is to push this into the quasi area at redshifts of 1 to 3 or even further. And that has become possible now too, because of further improvements in gravity to gravity plus. And this year we published a Nature paper showing the same kind of measurements, in this case of H alpha, and again this phase dip there of a rotating broadline region of a redshift 2.3 quasar, the size of 40 microarc seconds. And the key thing is that these objects here are Eddington limited quasars, so highly accreting objects, whilst of course most of the reverberation objects are low Eddington rates. And what we've learned now from the red data points there is that the high Eddington objects, including the ones at high redshift, seem to be more compact and somewhat lower mass in black hole mass than anticipated from the scaling relationships of the reverberation. And if that is the case, then I would say in a few years' time, we can establish a broadline region-based black hole mass, galaxy mass ratio at high redshift versus lower redshift, and thereby asking the very, very famous question of, what's chicken and what's egg, and how did the growth of the two come? I mean, it's early times for this, but I'm very, very confident that this is now possible. We just received last week, we made a measurement of another redshift 2.2 quasar, a very massive quasar, and again with a very compact broadline region size. Now let's talk about the evolution of these massive black holes. And of course, that goes back to many, many, many measurements. We know that there is the sort of the classical elliptical galaxy black holes, which dominate the highest mass systems. But then there's also, like in the Milky Way, the bulge-based, let me call them the bulge-based black holes in a disk galaxy, which don't have such high mass. The key characteristic that is, on average, if you select on the galaxy, the ratio of black hole mass to bulge mass is about a constant. It's varying a little bit, but not tremendously, independent of the accretion rate. And so that's a very, very important issue. And the question then, of course, comes about how did this co-evolution, which seems to be indicated here, actually take place? When did it happen? When did the growth happen? What was first? Now, the JWST, of course, has given us enormously interesting new information of ever higher redshift black holes. Here's the work by Roberto and his team on a redshift 11 quasar, and there are many, many, many such measurements. So high redshift that the discussion now is how can the classical Eddington limit accretion work so close to the Big Bang? And so that's why, in fact, as you probably know, the question of early black hole formation at or near the Big Bang has come back. The work which Stephen Hawking did already in 71 has come back. And here I show you, because I don't have so much time, a sort of a summary of the situation when you compare the prediction from the Carr et al. Paper of primordial black hole mass spectrum in dashed dotted black lines. So you can see there's a predominant plateau at low mass, maybe a peak at one solar mass, and then a small tail at high masses. So the key signature would be a high abundance of just sub-solar or near-solar mass black holes in our galaxies. And that has been tested very well already over the last years by microlensing experiments. And there's a paper from this year by Mross et al., which is this blue curve, excluding extremely well, I would have to say, any kind of a near solar mass peak. Could still be much smaller mass black holes, but definitely the Ogle experiment over 20 years' time makes the statement that they have not seen long enough long-term time scale microlensing events which could be caused by somewhat massive extended halo of black holes in the galaxy. So that's puzzling. It's puzzling because at the same time, and here I'm going to the third technique, the inspirals with LIGO have given us, of course, a ever richer spectrum of the stellar black hole masses and their combined masses, which show that the masses which are seen with LIGO, Virgo, and Kagra tend to be somewhat larger than you would have expected on the basis of the classical stellar population synthesis. Not 10 solar masses, but more like 20, 30 solar masses. And in fact, in this diagram here from the run 3, a few objects with a mass in excess of 100. So that means that the inspiraling objects were between 60 and 80 solar masses. Not many, and this measurement technique is biased because it's more sensitive to the very massive things. But the question is very, very important. How could it be that you have such systems where the individual inspiraling two objects, formally speaking, are in the pair instability gap? which shouldn't exist. So that's something which, of course, a number of people are working on from the point of view of population synthesis. Is it possible that the predictions were wrong? And of course, I'm eagerly, and I'm sure you are eagerly looking forward to more cases from the experiments. Now, it's possible, of course, that the higher masses here are not an outcome of the original explosions, but require a phase of accretion onto the to the black hole, which comes out in the first phase. And then if you have a dense enough region that, you know, basically you can have, like in the case of AGN, further growth, which then generates in some dense regions more massive black holes. We'll have to see how this exciting story continues. Well, let me finish here and sort of say I hope you would agree with me that we are in an absolutely fantastic time. I mean, what used to be speculations, we are now testing with, you know, very quantitative and sensitive tools. What we can do already now in terms of this parameter epsilon I introduced is to show that for AGNs through X-ray spectroscopy, through stellar black hole in spirals, and of course the galactic center, this epsilon parameter is less than 1. It's not 0, that we have not yet done, but it's less than 1. So how can we make progress? The first one is in the galactic center, if we get a star which has a pericenter radius not of you know, 120 astronomical units, but say of 50 or 40, then we can measure the higher ppn order parameters and the spin. Likewise, in the galactic center, if you had better resolution or higher frequency measurements of the event horizon measurement, and in fact even see the spikes, that would go a long way of getting a very sharp statement on the mass itself. If there were a pulsar in the central region, which of course many people have looked for a long time, that would make things even better. So if you had a combination of that and then spectroscopy with the ELT, which can go to significantly higher ppn orders through spectroscopy, well, then we can measure the quadrupole moment, make a test of the air theorem, and then put it all together, and maybe then indeed for the galactic center set a strong limit on any deviations from parametric and no hair. Ultimately, I'm putting my money, of course, on LISA, because LISA is in a unique situation, if it works, of measuring extreme mass ratio in spiral, where the last orbit before inspiraling into a common black hole happens over a long period of time, unlike the stellar black holes, where this is less than 100 milliseconds, where it's very difficult to get enough signal-noise ratio. In the case of LISA, we're talking about days, and thereby the predictions predict limits on epsilon of 10 to minus 3 or 10 to minus 4. If you can do that, wow, that would be just absolutely fantastic. But as it is, I must say, at the end of my career, I'm very pleased how this field has come from really a true speculation and discussion of whether black holes exist at all to actually testing the Schwarzschild curvature. Thank you very much.